So we've mentioned the background radiation that we're exposed to all the time. Let's look at that in a bit more detail. Now, in Australia, the average person is exposed to about 1.8 millisieverts per year on average, which is pretty small. It's a thousandth of the dose of 1 sievert, which would give you a 5.5% chance of dying. Where does it come from? Well, about 0.6 millisieverts of it comes from the rocks below our feet and the buildings around us. That there are trace radioactive elements in the ground beneath us and often in the building materials we use to build our buildings. Very tiny amounts, but there's a bit of radiation coming from them. 0.5 millisieverts comes from radon gas. So remember that radon gas and its decay products are produced when in the chain of decay from uranium-238. So again, there's uranium-238 at very low concentrations in almost all the rocks, though it's more in some rocks than others. And as it decays, it produces a whole chain of different decay products, one of which is the radon gas. And this being an inert gas, it can often escape from the rocks and make its way into our buildings, and we can breathe it in. And that gives us 0.5 millisieverts per year of radiation. There's about 0.4 which is coming from actually our own bodies. So in our own bloodstream we have potassium-40 and small amounts of uranium and thorium, and these all have very long half-lives, but they do decay. This is a radiation we carry around with us. So in fact, if you sleep next to somebody, you're getting radiation from them, from all the potassium-40, uranium and thorium in their bodies. And then about 0.3 millisieverts comes from cosmic rays that penetrate the Earth's atmosphere. There'll be more if you're up at higher elevation, like top of Mount Kosciuszko. It's probably a bit higher in Canberra because we're at 600 meters above sea level. Now, does this kill people? Now remember, there are no reliable stats for doses of less than 100 millisieverts. But if we assume the linear no-threshold model, then we can do the calculation. So let's imagine you live 50 or 60 years at a dose of 1.8 millisieverts per year. That gives you a total dose of about 0.1 sieverts. And according to the linear no-threshold model, that's 1/10 of the 5.5%. So it's about a 0.5% chance of dying due to radiation-induced cancer. So does that mean 0.5% of us, 1 in every 200, are dying because of background radiation? Well, we know that cancer kills about 20%. So this can't explain all the cancer. 0.5% can maybe explain 1/40th of the cancer. And it could be that 1 in 40 cancers are indeed due to background radiation. Or maybe not. Maybe the no-threshold model is incorrect. The body can actually repair small amounts of damage, and instead of 19.5% of people dying from cancer, all 20% is caused by cancer from other causes. We don't know. Background radiation varies from place to place. The main difference is due to radon gas and its decay products. It's all around us, but it depends crucially on what sort of rock your building is built on and whether the gas leaking out from the rock concentrates in the buildings. So this depends on what geology is underneath your rocks, and also whether the rocks have porous floors, so that sucks the air in, and poor ventilation, so it concentrates. In the US, often people have radon detectors to take around their houses to make sure that radiation levels are quite low. Australian homes tend to have low radon levels whenever it's been tested. But there have been cases, I remember once doing a visit to a UK nuclear power plant, and they had nuclear scanners when you leave to make sure you didn't pick up any radiation, but they also had nuclear scanners for when you went in, because they found a small fraction of people were highly radioactive when they went in to visit the nuclear reactor, because they lived in a home with a high radon. Maybe their house was built over a uranium vein, maybe buried deep underneath the ground, and there were some people who had quite high radiation doses coming in that actually triggered the alarm and shut down the entire nuclear plant. But generally in Australia it's quite low. It tends to be higher in some of the higher inland areas where there's just more radon in the rocks underneath. And it's been mapped. Now, flying increases cosmic rays. A flight to London exposes you to about 0.04 millisieverts, basically because you're higher up and therefore get more cosmic rays. Now, this is an extremely small dose for someone who flies there once a year, but if you're a frequent flyer and spending a long time in flights, especially flights that go over polar regions where there's more cosmic radiation, it could be a problem. It's particularly a problem for flight crew and frequent flyers. And then you get more radiation from medical x-rays, about 0.05 millisieverts for a dental x-ray, but more for like a chest x-ray because it affects more of your body, and CT scans give about 5 millisieverts. And the worst thing for radiation exposure is being an astronaut, because when you're above the atmosphere, the radiation doses are very high. This is a big problem for long-duration spaceflight. A curious fact is that in the USA, most alcoholic drinks are tested by the government for radioactivity, and they're only allowed to be sold if they are radioactive. Why is this? Well, they were worried that people would be producing things like gin alcohol from petrol, from petrochemicals. And they use the radiation as proof that it's actually natural, because natural alcoholic drinks are made from plant material, and plant material draws its carbon from the atmosphere. And carbon in the atmosphere has a small fraction of carbon-14 because of radioactive cosmic rays hitting atoms in the upper atmosphere and converting carbon-12 into carbon-14. And this is then incorporated into plants. It's got a half-life of about 5,000 years, and so any food or beverage that's been made from actual living material will have small amounts of carbon-14 and therefore will be radioactive at some level. For example, a banana is about 0.01 millisieverts. If, however, someone has produced food or alcohol artificially from petrochemicals, the petrochemicals were made from wood originally, but it's been buried underground for 200 million years, so all the carbon-14 will have long gone. So if you have non-radioactive alcohol, you know it's artificial, it's been made from petrochemicals. Legal limits in Australia. For the general public, the limit is 1 millisievert per year, not including the normal background level and not including medical procedures. If you work in the nuclear industry, radiation exposure is allowed to be up to 20 millisieverts per year, averaged over 5 years, and has to be less than 50 millisieverts in any 1 year. So you can't have like 100 millisieverts in 1 year and nothing for the next 4. That's not allowed because that would go over the limit.